In the first part of this tutorial, we looked at bounded and monotonic sequences, and we also saw that the sequence an equals 2n is divergent, which means it doesn't converge to a finite limit. In this second part, we'll look at what it means for a sequence to be convergent. So now let's move on to sequences which tend to a finite limit. In this definition, this value a is a number which has some finite value. In other words, it's not infinite. So here's the definition. The idea is that for any positive real number epsilon, no matter how small, we have to be able to say that it's possible to find some natural number n of epsilon such that the modulus of an minus a, in other words the positive distance between an and a, is smaller than epsilon, provided that n is greater than or equal to n of epsilon. And in this case we write that the limit of an as n tends to infinity is equal to a, which is the same as saying that an converges to a. So this definition might look slightly more complicated than the definition of a sequence tending to infinity, but it's really the same sort of principle, and we'll see how this works with an example. So let's look at another sequence. In this sequence, every term from the second term onwards is half of the term before it, and the general rule is an equals a half to the power n. So here's our sequence, a1 equals a half, a2 equals a quarter, etc. And as the sequence goes on, the terms get smaller and smaller. So for example, we have a8 equals 1 over 256. And if you had to say what happens to the terms in the sequence as it goes on and on, you'd say that the terms approach a value of 0. In other words, the sequence tends to 0 or converges to 0. So it's all very well being able to recognise that from the diagram, but how can we actually prove it? Well, just to recap, this is what we have to do. We have to show that for any value of epsilon, no matter how small, it's possible to find a natural number n of epsilon, which depends on epsilon, such that this inequality, the modulus of an minus a is smaller than epsilon, holds whenever n is greater than or equal to n of epsilon. So just think of epsilon as being some very small number, and the idea is we have to show that there's going to be a point in the sequence where all of the following terms will be within a distance of epsilon from this value a. And in our example, an equals a half to the power n, and a is 0, because we're trying to show that the sequence tends to 0. And the way we're going to do it is we're going to start with the inequality, the modulus of an minus a is smaller than epsilon, and we're going to rearrange this to make n the subject, because that will tell us how large n needs to be in order for this inequality to hold. So in a way it's a bit like we're working backwards. So if we write down the modulus of an minus a is smaller than epsilon, that's equivalent to saying the modulus of half to the power n minus 0 is smaller than epsilon in our particular example, and that's the same as saying a half to the power n is smaller than epsilon, because a half to the power n is always positive, so we can remove the modulus signs. Now if we take logs of both sides and use the rules of logs, we can say that n times the natural log of a half has to be smaller than the natural log of epsilon. And finally, this says that n has to be greater than the log of epsilon over the log of a half. So notice that the inequality sign has changed because we divided by the log of a half, which is actually a negative number. So the conclusion is that if we're given any small value of epsilon, we can choose n of epsilon to be any natural number which is greater than the log of epsilon over the log of a half. And then we know that whenever n is greater than or equal to n of epsilon, this inequality is going to hold, and that's the result we need. So just as an example, suppose we're given a small value of epsilon, for example 0.001, then if you work out the log of 0.001 over the log of a half, it gives a value of 9.97. So we can choose n of epsilon to be the next natural number up, which is 10. And just to check, if you work out the value of the modulus of an minus a, which is just a half to the power n, it gives roughly 0.00098, which is smaller than 0.001 as required. Now let's go back to our diagram. Let's imagine that epsilon is some small number, and let's draw two horizontal lines. So the top green line is at 0 plus epsilon on the vertical axis, or just epsilon, and the bottom green line is at 0 minus epsilon, or just minus epsilon. Now you can see that if one of our terms, an, is in between the two green lines, then that means its value is between 0 minus epsilon and 0 plus epsilon, which means that the modulus of an minus 0 is smaller than epsilon. These two statements are exactly the same algebraically. Now suppose we draw a vertical line here, and this is going to show the value of n of epsilon. So the way we've drawn the diagram, we have that n of epsilon is equal to 6. And you can see that all of the terms in the sequence from this point onwards are going to be between the two green lines. And that's really what we're trying to show. We're trying to show that no matter how small you make epsilon, you can find some point in the sequence where all of the terms from that point onwards will be within a distance of epsilon from the limit value, which in our case is 0. So in our diagram, with the value of epsilon we've chosen, it turns out that all of the terms from the 6th term onwards will be between these two green lines. Now remember that we have to be able to show this is true for any value of epsilon, no matter how small. So if you imagine what happens if epsilon gets smaller, that's going to mean that the two green lines are going to get pushed closer together. And that's going to mean that we're going to need a larger value of n of epsilon to find a point where all of the remaining terms are within the green lines. So the general rule is, the smaller epsilon gets, the larger n of epsilon needs to be. Thanks for watching this tutorial, and look out for the next one coming soon.